everyone, and welcome back to Learning at 11th Hour. Today, we are going to look at some problems related to Norton's theorem, which involve dependent sources in the circuit. Let's move on to the first problem. So, here we have a voltage dependent voltage source present in the circuit. In that case, how do we progress and obtain the Norton's equivalent circuit? So, as we always do for Norton's theorem, we are going to identify the output terminals. In this case, this is given as AB, and there is no load connected here. If there were to be a load connected, we would remove it and then we would short circuit it. Then we need to compute the short circuit current ISC flowing between the terminals AB. Now, if we look at this circuit closely, since there is a short circuit over here, there would be no current flowing through the 2 ohm resistor because current is going to take the least resistance path. So, therefore, we can actually ignore this 2 ohms on a whole. Also, since the terminals A and B are shorted, the voltage across AB is going to be 0, which is nothing but the voltage across the 2 ohms resistor, since both of them are parallel to each other. So, therefore, Vx is also equal to 0. So, now I can redraw this circuit. In this case, I will have the 6 ohms resistor here with the 10 amps current source, and in this case the dependent source value is actually 2 times Vx. If Vx is going to be 0 over here, then 2 times Vx will also be 0, which means that is also shorted. There is no 2 ohms resistance because it can be ignored due to this short circuit. Since there is a short circuit between the terminals A, B, across which the 10 amps source is connected as well as the 6 ohms source is connected, this 10 amps is going to take the least resistance path. It is not going to enter the 6 ohms at all. So, therefore, we see that ISC, or the short circuit current, which is nothing but the Norton's current, is the 10 amps coming out from this current source. So, this was our first step. The second step is to obtain Rn. So, in order to do that, we need to remove this short circuit first. We then need to kill the independent sources too. So, independent source, if it's a current source, we are going to open circuit it. If it's a voltage source, it should be short circuited. In this case, we have a current source, so we need to open circuit it. Let's redraw this circuit. So, we have 6 ohms. Then the current source is open circuited. We have the dependent voltage source of 2Vx. We have the 2 ohms across which the drop is Vx, and this is our output terminal AB. So, just as we used the test source method for obtaining the Thevenin's equivalent circuit if the circuit had dependent sources, here also we are going to apply the test source method. In case of Thevenin, we used a 1 amp test source. So that was a current source. In this case, we are going to use a 1 volt voltage source as my test source. Then I'm going to try and find out the current I. If I manage to find out the current I coming out from this test source, then from Ohm's law, I can say that V by I is the total resistance of the circuit, which in turn is the resistance looking in from the terminals AB, or in other words, it will be my Norton's resistance. So, my objective is to obtain the value of I. So, looking at this, let's assume this is how I flows, and say there is a loop current of I1 flowing through this loop. So, this is I and this is I1. Now, let's apply KVL to my first loop. So, here I have 2 into I minus I1 is equal to 1 because we have I flowing from terminal A to terminal B, whereas I1 is flowing from B to A. Let me call it as A dash and B dash. Now, we can obtain the second KVL equation by applying KVL to the second loop. So, what we get here is plus 6i1 plus 2i1 minus I, because this is the drop and this is the assumed direction. Both are in the same direction, whereas the current I is opposing it. So drop due to I will be minus, and this drop due to the dependent voltage source is also opposing the assumed direction. So minus 2 times Vx is going to be equal to 0. So now here, what is Vx? Vx is nothing but the voltage drop across the terminal A dash B dash, which is nothing but the drop across the terminal AB, which in this case is the value of the test source. So we know that Vx is equal to 1 volt. So we can replace that over here, and ultimately we get 8i1 minus 2I is equal to 2 times of Vx. And this is my second equation. So on resolving both the equations, right, I would be able to obtain the values of I and I1. So how do I do that? So this is 2 uh, I minus 2I1 is equal to 1, and I have minus 2I from the second equation plus 8I1 is equal to, since Vx is 1, I'm just going to keep it as 2 over here. So when I solve this, suppose I add both these equations, so this would go out. So this is 6i1 is equal to 3. Therefore, I1's value is going to be equal to 1 by 2 amps, zero point 0.5 amps. Now, when I replace the value of I1 over here, I will get the value of I to be 1 amp. So therefore, I can say that Rn is going to be nothing but V by I, where V's value is 1 volt, I's value is 1 amp. So therefore, I'll get it as 1 ohms is equal to Rn. So now that I have obtained the value of ISC, or the Norton's current source value, as 10 amps, and the Norton's resistance is 1 ohm, I can now draw the Norton's equivalent circuit as ISC, whose value is 10 amps, and Rn, whose value is 1 ohm, across the terminals AB. So moving on to the next problem. Here again, we need to obtain the Norton's equivalent circuit for this. Here we have a current dependent current source. How do we progress? So the first step is to short circuit the output terminals. If there were to be a load, I need to remove it and then short it. Then I need to compute the value of ISC flowing through the terminals AB. So in order to do that, I can find the node voltage VA. But before we do that, if we observe the circuit closely, so the 10 volts and the 4 ohms, they are parallel to each other, but they are also parallel to the 5 ohms and this dependent current source. How is that? That is because the points A and B have the same voltage, and they are one and the same as these 2 points too. So therefore, you can see that the 10 volts and the 4 ohms are connected over here, which is nothing but point B, which is nothing but point A, which is nothing but, I'll call this as B dash A dash B dash. So in this case, A dash is B dash is A, which is B. If I call this as C dash, which is nothing but C and C dash. So all of these points are actually one and the same. That is because there are no other extra elements connected in these wires. So we can actually redraw this circuit as 4 ohms with the 10 volts over here. So this is C dash, this is C. Now I can draw this 5 ohms in this manner, where it is connected to B dash, which is nothing but B. So this is 5 ohms, and this is the dependent current controlled current source. Here, the value of Ix is the current flowing through the 4 ohms resistor. If we manage to find out the node voltage VA, we will be able to obtain ISC. by applying KCL at node A. So, how do we progress? In this case, first let's compute the value of Ix. Ix is nothing but the current flowing through this 4 ohms resistor, which is 10 divided by 4. Why? Because the voltage across this 4 ohms is nothing but 10 volts. So, therefore, Ix is equal to 10 divided by 4 amps. Again, the 5 ohms is also connected across this 10 volts voltage source. So therefore, I can say that the current flowing through this is also going to be 10 by 5. So now, if you look at this node A, if we apply KCL at node A, so there are two currents entering here. One is the current flowing through the 5 ohms resistor, which is obtained as 10 by 5 or 2 amps. So there is a 2 amps flowing in, and then there is a 2ix flowing in. So 2 plus 2ix is equal to the current which we need to obtain, which is ISC. So therefore, this current plus this current is the current flowing through the AB terminals, shorted. So therefore, what is Ix in this case? Ix is nothing but 10 by 4. So I can replace that value as 2 into 10 by 4. So that means ISC is nothing but 7 amps. The next step is to obtain the Norton's resistance, Rn. So in order to do that, we need to first remove the short circuit, and then we need to kill the sources, ensure that only the independent sources are killed, the dependent sources will remain as it is. Then we need to apply the test source method. So let us now compute Rn. So I have removed the short circuit. Now I need to redraw the circuit after killing the sources. Since this is a 10 volts voltage source, I will have to short it in order to kill this source. I have to retain the dependent current controlled current source. So on redrawing, I will be able to obtain a circuit with the 4 ohms intact, short circuited voltage, independent voltage source. This is my 5 ohms. This will remain as it is, 2Ix, where Ix is nothing but the current through the 4 ohms. And this is followed by connecting a test source of 1 volt across AB. Now, since this is shorted, I can simply say that we can ignore this 4 ohms, because whatever current that is going to flow, it is going to flow into this branch. It is not going to split up and go into the 4 ohms, because current is going to take the least resistance path. Therefore, can I say that Ix is going to be 0 in this case? And if that is the case, then 2Ix is also going to become 0. So therefore, the circuit merely boils down to something like a 5 ohms with 1 volt, the test source that is connected in this manner. Now, my objective was to obtain Rn. I know the value of V. If I'm able to compute the value of I will be able to find out Rn as V by I. So here, what is the value of I? I is nothing but 1 by 5, which is I. So therefore, I can say that Rn is nothing but 1 divided by 1 by 5 ohms. So that is 5 ohms. So this becomes the resistance looking in from the terminals AB. So I can now redraw this entire circuit using the Norton's equivalent circuit. So this is how it will appear. So here we've obtained our ISC as 7 amps and Rn as 5 ohms, which means my entire circuit over here can be redrawn as 7 amps in parallel with the Norton's resistance as 5 ohms connected across the terminals, output terminals AB. So that's all with today's video. So hope the test source method, in case of circuits having dependent sources is clear to you all. This will be useful in obtaining the Thevenin's equivalent and the Norton's equivalent circuit when the circuit has a dependent source in it. Thanks for watching this video. Please do subscribe to my channel. Please do subscribe to my channel for more such videos. Bye bye.